goes in here, and how much the light bends depends on how fast the light travels here and how fast the light travels here, called the refractive index of this material. And Dave is going to show you some tricks about what can happen when you match refractive indices, with the refractive index between two different mediums.
Now, in one hand I have a hammer, in the other hand I have a test tube. What do you think I'm going to do? Yeah, right. We have so much fun here. Smash them up, smash them up. Like I said, it's amazing they pay me to do this, but what can I say? So we're going to pour this all in here, this magic liquid. And we need a magic word. What do you think the magic word in the physics show should be? What is the magic word? Physics, right? So we all need to say physics. Does anybody want to buy this? What we have is we know that the refractive index of the test tube is exactly the same as the mineral oil, baby oil. So inside there I already had a test tube. Okay, so I smashed it up and put it inside and then pulled out the one that was still inside. It's the exact same index of refraction. And I'll prove that to you with this. Focus this up a little bit better. Doing things very quickly, so turn this. Hard to do this way. Okay, you see that beaker on the inside, right? Yeah. Excuse me for a second. There you go. And what I'm going to show you is that it's not just mineral oil, but it's also vegetable oil that has the same index of refraction. So I go ahead and I pour this on the inside beaker. You still see that inside beaker? Yeah, you still do, right? No problem. But let it go around the outside. You still see that inside beaker? Easy to buy this one.
Instead of pulling in, blows out. Actually, my wife is convinced that that's the way I always learn about it. This guy blows out. You're not surprised when I put him on here, he gets blown upward. The surprising part is that when he gets blown upward, he doesn't fall off. He doesn't fall off because if he goes off to one side, the air rushes by. Over here it has a high speed, low push. Here it has no speed, big push, and it gets pushed back in. So the Bernoulli effect keeps it in the stream. And he stays up there very nicely. You can even tip a great deal.
I'd make it go down. What can't I do?
Another cube with it. I'll set up the temperature. 1, 2. Now we're going to do a series of demonstrations here, some of which will involve the following. Nate, can you guys work in the dark? Yeah. Can you see these slow things moving around over here? Yeah. Okay. These are supposed to be gas molecules, like the air around you. I want you to now think about the air around you when it's hot and when it's cold. And when the air around you is really hot, this is the situation right here. The air molecules are all moving much faster, and when it's very cold, they have slowed down and they're going much slower. So there's a direct correlation between how fast the air molecules, the individual pieces of the air are moving, and what the temperature is. Of course, there's also going to be a correlation to the push they exert on the wall. If something is moving very fast and hits a wall, it pushes on the wall very hard. If something is moving very slow and bounces off very slowly, it pushes on the wall with a very little push. And so that you can have a high pressure on the wall over here and a lower pressure on the wall over here. This is a microscopic way I want you to think about hot and cold gases as we do things. Now we're ready to go, right there?
Yeah.
Which one?
Oh, does this sink or does it float? Opinion. What do scientists do? They try things, right? They do experiments and they try things and then they look and see what happens and then they decide, okay, maybe this is what happened, maybe it's not what happened, but they try to figure it out by trying things. They try experiments. So let's try the experiment. The bath of water. I put the Coke in here. What does it do? What's this? What do you think? Who says it sinks? Who says it floats? Should we do the, we're scientists, right? We just proved it. We just did the experiment. Should we do another one? Get that one out of the way. And it does. It floats. Now that we're scientists and we saw that, we have to try to figure out, okay, what exactly is happening there? Did they put less soda in this one? Did they put more carbonation in that one? No. This is sweetened with high fructose corn syrup. Not sugar. Nothing's sweetened with sugar anymore. And this has Splenda in it. So a soda that's sweetened with Splenda needs a lot less Splenda than the high fructose corn syrup that's in the other soda. So it's actually more dense inside that other soda. So the same volume of soda, but it's actually a little more dense, so it sinks in water. Now ask yourself this.